In this video, I've mixed up some topics that appear in the other sections, as well as just taking the chance to talk about a couple questions in 6.6. Section 6.6 is really just extra counting problems. It combines rules. We've already actually seen a couple of selected questions from 6.6. But again, I wanted to just kind of give a wrap up and give you some ideas of things to look for. So one thing we didn't talk about in the first permutations video is permutations with repeats. The most common application of these is things like the question you see above. How many ways are there to arrange the letters in the word hello? So I'm going to write down maybe your first idea, and let's actually answer this question. You say, well, there's 1, 2, 3, 4, 5 letters there, so you might think automatically there's 5 factorial ways to arrange them. But the problem is these two L's, I can't really tell the difference between. So in the end, however you arrange them, these two L's are difficult to distinguish. And so when you think about that, that's the repeat. And so we want to divide that up. So the actual answer to this, and I'm not going to simplify it or anything, is 5 factorial over 2 factorial. And so again, anytime you're doing this, you always end up dividing by the repeats. So another common one is MISSISSIPPI. All right, how many ways are there to arrange these? Well, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 11 factorial, except now you got to account for the repeats. So the letter I is repeated 1, 2, 3, 4 times, so divided by 4 factorial. But the letter S is repeated 1, 2, 3, 4 times. So you got to account for that. So again, another 4 factorial. And then finally, we didn't miss anything, did we? Oh, yeah, we did. There's 2 P's, and so now we got to account for that. 2 factorial. So this pattern will always continue, and it has some interesting applications. So I don't plan to ask you much more beyond this. But this is actually a problem that I've had several times as a bonus question. And it says, how many paths are there from A to B, where a path would be something like this, where I can go down here, I can go like this, and then I can go like this. And it's all about how you view a path. For instance, what I could do, this path I just took, I could view it in this particular way. I could say, well, I went down, then I went right, and then I went 1, 2, 3. I went down 3 times. So down, down, down. And then when I went right twice. Now, any path that I take, and this is something for you to double check. Like I said, I'm not going to do this problem since it's been a bonus question so often. 1, 2, 3, 4, 5, 6, 7. Any path I take will have to have 7 moves like this. One would be, for example, going down and then all the way over, right? So it'd be 1, 2, 3, 4 D's, and then 1, 2, 3, 3 R's. And in the end, no matter what path you take, you have to go down 4 times, and you have to eventually go to the right 3 times. So this could be considered an arrangement of these letters. And so when I say how many paths from A to B, really what I'm asking is how many arrangements are there of these letters right here. And so this has surprising applications, so it's worth a brief mention. Now, another thing that's worth mentioning is when you talk about the total number of subsets in a set. So here I say, how many subsets of the set ABC are there? So ABC, let's just think about this particular set. So if this is A itself is a subset. So here's the first subset, the easy one. Right? The next easy subsets to think of are the one-element subsets. So you could have the 3-element subset, the 1-element subsets, and then what else could there be? 2-element subsets, right? We could have the subset AB. We could have the subset BC. Right? So AB, BC, and then what else? AC. So we got 1, 2, 3, 4, 5, 6, 7. Well, we didn't quite think of everything. So did we cover everything obvious, though? Yes, there's only one left. And that's the null set, which is the subset of everything. Now, in general, you can actually find the number of subsets to be 2 to the n power. So for any set, the total number of subsets is 2 to the n power. And this actually comes from thinking about all the possible combinations. So in other words, we say, well, right here, I'll write it up here actually. This was the number of ways you could arrange 3 things out of 3. That's the number of 3-element subsets. And if order doesn't matter. So this is actually equal to 1. This right here is how many 1-element subsets are there. There's 3. This right here is how many 2-element subsets are there. Well, there's 3. 1, 2, 3. And this right here is how many 0-element subsets are there. And then there's 1. And so what this actually does is if you took, for instance, if you started with 5 and you did C of 5, 5, 5, 4, 5, 3, 5, 2, 5, 1, 5, 0, you did all those combinations, add them up, you'll get 2 to the 5th. And so this actually comes from that, and you can actually see that in Pascal's triangle, a very interesting mathematical object. So this is worth a mention. Sometimes this is useful in some of the advanced counting problems, so you should kind of set it aside for yourself. We might not see anything too direct with it, but it's worth making note of. So as I mentioned, a big thing in 6.6 is just mixed up problems that use all kinds of techniques. And so I wanted to show you a couple. I just selected these kind of randomly. In the end, just like I've said before, I can only show you so many examples. You have to do enough problems to recognize the patterns. So this tells us a social security number has 9 digits. Repetitions allowed. So we're going to assume you could have the social security number 000000000. Probably can't have that, but based on this, we'll just say, okay, that's allowed. How many social security numbers have at least 1 repeated digit? So the one I said just had all repeated digits, right? So at least 1 repeat means you might have 1 repeated digit, or 2, or 3, or 4, or 5, all the way up to 9. So the problem with that, and the reason I state it that way, is because OR means addition. So that means I'd have to count all of the numbers, all the possibilities with all repeats, all the possibilities with 8 repeats, all the possibilities with 9 repeated digits, or 8, 7, 6. I mean, in the end, I'll have to think about all these cases. But if I can view it a different way, I can save myself a lot of trouble. So I have to sit there. Does this make sense? What does it mean to have 9 repeated digits? I don't want to have to worry about this. So if you think about it, what is this set actually? If we think about all the social security numbers allowed based on this rule, what if we were to subtract those with no repeats? All social security numbers based on this, how many there are, easy to count. Those with no repeats, easy to count. What's left over? Those with at least 1 repeat. So a very different viewpoint, a very, very different viewpoint. So think about how many social security numbers are possible. Okay, so we have 9 digits, repetition is allowed. So if I think about it with the multiplication rule, I say, well, we could have 9 spots. I'm not going to write them out. Each would have the number 10 in them, right? Because you could have any one of the 10 digits. So in other words, this is 10 to the 9th power. 10 to the 9th power. And then we say, well, how many would have absolutely no repeats? So that's all unique numbers. So that's basically starting with 10 and counting down. In other words, this is permutation of 10, 9. Okay, so when I do this subtraction, I should have the number of those with at least 1 repeat. So 10 to the 9th. And then I, again, subtract the permutation. And remember, try to put parentheses just as a good habit. And I get a large number. I get 996, 371, 200. So let's see. A large number, but not as large as I expected personally. But again, counting this directly, practically impossible. You'd have to think of a lot of different cases, and you'd have to reason out what the problem represents exactly. Whereas if I view it from this perspective, what's left over, much, much easier. So again, you got to start practicing so that you can see those kinds of things. Let's look at one other interesting problem. So in this one, we're told that a scout troop has 22 members. We want to appoint a 5-member crew. They'll have a leader, a chef, and a cleanup crew. Okay, as soon as I see names on them, a leader, a chef, so I'm thinking order matters with those. But then it says a cleanup crew of 3 scouts. Okay, so there's no labels there, so order doesn't matter there. How many different crews are possible? So this right here, and, is telling me something. I'm going to probably have to multiply here. So let's think about it. The part that order matters would be the leader and the chef. And then you want your crew. Okay, so let's think about the leader and the chef first. There's 22 members. So this is order matters here. So this is 22. And permutation because order matters and you're picking 2. And then the cleanup crew order doesn't matter, but how many people are left? There's only 20 left. So this would be a combination. Out of 20, you are now picking 3. And actually, if you did this in the other order, you'll get the exact same answer, but your numbers will look a little bit different. So when I calculate this, I get 526,680. So let's write it down, 526,680. So again, a very large number, but that's because of that first part where order mattered. That's going to increase the number of possibilities by a lot. So again, as you go through 6.6, realize there's nothing new there. It's just giving you some extra counting techniques and some practice. And so it's worth going through the practice problems, but there's nothing necessarily new to learn, just a variety of problems to see in practice.